Hey, tech trailblazers, it's Lucy here, and we've got massive news from the quantum computing world. After 20 years of chasing it, scientists have finally cracked magic state distillation on logical qubits, a breakthrough that could make quantum computers error-free and more powerful than any supercomputer. This just dropped in a study published July 14th, 2025 in Nature, and it's a game changer for everything from AI to biotech. Buckle up because we're diving into what this means, why it's huge, and how it brings us closer to quantum supremacy. Let's quantum leap into it. First, let's break it down. Quantum computers use qubits. Think of them as super-powered bits that tap into quantum mechanics like superposition and entanglement to crunch data crazy fast. But here's the catch. Qubits are super sensitive to noise like temperature spikes or rogue photons, which mess up calculations. That's where magic state distillation comes in. It's like refining crude oil into jet fuel, taking noisy, imperfect quantum states and purifying them into high-quality magic states. The secret sauce for running complex quantum algorithms. Until now, scientists could only do this on error-prone physical qubits, not logical qubits. Groups of physical qubits designed to catch and fix errors. This new study from Kira, Harvard, and MIT changes everything by pulling it off on logical qubits for the first time. So, what does that mean? Imagine you're trying to send a message across a noisy room. Physical qubits are like shouting over the noise, errors creep in. Logical qubits, on the other hand, are like having a team of friends repeat your message, catching and correcting mistakes along the way. Magic state distillation on logical qubits means we can finally send those complex, delicate messages with way less risk of them getting garbled. This is a huge leap because it brings us closer to building quantum computers that can actually solve real-world problems, not just toy examples in a lab. So why is this a big deal? Quantum computers need to run non-Clifford gates, fancy operations that unlock their full potential to outpace classical supercomputers. The problem? Most error-correcting codes only let you use Clifford gates, which are basic and can be simulated on a laptop per the Gottesman-Nil theorem. Magic states are the key to non-Clifford gates, but they're super hard to make with low errors. The old way, distilling magic states on physical qubits, was like trying to build a rocket with shaky parts. You could get it off the ground, but it was risky and inefficient. Now, Kira's team used their Gemini neutral atom quantum computer to distill magic states on logical qubits, which are way more stable. They ran a 5-to-1 protocol, turning 5 imperfect magic states into one super clean one, with fidelity beating any input. This means quantum computers can now run complex algorithms with fewer errors, paving the way for real-world applications like cracking encryption or designing new drugs. Imagine a future where quantum computers help us discover new medicines in days instead of years, or break codes that are currently uncrackable. That's the kind of power this breakthrough unlocks. And it's not just about speed, it's about reliability. With logical qubits and magic state distillation, we're talking about quantum computers that can actually be trusted to deliver accurate results, not just theoretical promise. Now let's get into the nitty-gritty. The team used Quera's Gemini neutral atom quantum computer, which manipulates atoms with lasers for crazy precision. They grouped atoms into logical qubits using distance 3 and distance 5 color codes. Think of these as safety nets that catch 1 or 2 errors, respectively. The bigger the distance, the better the qubit, as Yuval Boger from Kera told Live Science. They ran a 5-to-1 distillation protocol, where 5 noisy magic states were combined into one high-quality state. The result? A magic state with higher fidelity than any of the inputs, proving this works in practice. Plus, the Gemini's dynamic reconfiguration let them process multiple logical qubits in parallel, making it super efficient. This is a huge step towards scalable, fault-tolerant quantum computers that can handle massive calculations without crashing. The Gemini system's flexibility means researchers can quickly adapt to new protocols and scale up as needed. It's like having a quantum computer that can rewire itself on the fly to tackle whatever problem you throw at it. And the collaboration between Quera, Harvard, and MIT shows just how much momentum there is in the field right now. We're seeing breakthroughs not just in hardware, but in the algorithms and error correction techniques that make quantum computing practical. Now, it's not all smooth sailing. Magic state distillation is still resource heavy, requiring lots of qubits and time. Sergio Cantu from Quera told Live Science that quantum computers need low error rates to run long, complex calculations without turning into mush. This breakthrough shows it's possible, but we need more rounds of distillation and better hardware to scale up. The study also hints at exploring other methods like magic state cultivation to cut costs further. The good news? This milestone, combined with earlier error correction wins from Google and others, means we're closer to quantum computers that can outdo supercomputers for real-world problems. The race is on, but there are still big challenges ahead. Scaling up to thousands or millions of logical qubits will require new engineering solutions and lots of innovation. Researchers are already looking at ways to make the process more efficient, so we can get to practical, everyday quantum computing sooner rather than later. This magic state distillation breakthrough is a massive leap toward fault-tolerant quantum computers that can change the world. From cracking unsolvable math to revolutionizing medicine, the possibilities are endless. Are you hyped for the quantum future? Drop a comment, smash that like button, and subscribe for more cutting-edge tech updates. Let's keep exploring the quantum frontier together.